Thanks, Steve. All right, good morning. And I think I'm between you and break, so I'll try to keep it moving along and get you to your break on time. Okay, so I'm going to be talking to you about lessons in resiliency and incident response at Shopify, and in particular on some lessons we learned during Black Friday last year. So just to give you a bit of context, so Shopify, for those who aren't familiar, is a software platform for retail. So we provide the software for over 500,000 online stores, but also retail, physical point-of-sale devices in stores. So basically all the software you need to run a store. So obviously Black Friday is a big deal for us. And yeah, so I'm going to talk about these two concepts of resiliency and failures. So a very simplistic way to think about this is resiliency good, failures bad. Okay, so that's a very simple way of thinking of things. And I'm going to try to convince you that's the wrong way to look at it. And what you want to think of as failures as great. I love failures because failures teach me new things about my system and help me to learn how to make it more resilient. And what we actually want is a system that fails all the time, but nobody, or at least your customer, does not notice. So this tends to be a very, people have talked about this before, and it tends to be very kind of hand-wavy and abstract and sounds simple in theory, but hard in practice. So I thought I'd do this by taking you through a couple of actual incidents that we had during a very critical period, and how the systems responded to those failures and adapted. So the very first principle I'm going to talk about 4 different principles. The first one, very simple. If it can break, it will break. So it's not worth spending much time thinking about, how can we avoid this thing breaking? What you should be thinking about, yep, it's going to break. We need to make sure that when it breaks, our system responds to that properly. So just to set the stage a little bit, so Black Friday, if you're mostly a North American audience, it's the start of the holiday period. The traditional origin of the word apparently is that Black Friday is when the red ink of loss turns into the black ink of profit for a retailer. And for many retailers, really this holiday period, especially online retailers, the 2 weeks from Black Friday really is a make or break week for the entire year. And for a smaller business, it can be the difference between continuing on to the next year or folding up shop. So it's a very, very critical period for our merchants, and is something that we take very, very seriously. So we spend quite a lot of our year preparing for Black Friday. So I'm not going to talk too much in detail about our plans throughout the year, but we spend most of our years oriented towards a successful holiday period. Just to give you a very small flavor of it, our director of production engineering said, I want everyone on call to be in a place with multiple sources of redundant internet access. So the IT team built him this hat with an LTE hotspot and a battery pack on it. So he could walk around anywhere in the world or anywhere in North America and have redundant internet access. So a little bit tongue-in-cheek, but the idea there is we want to be prepared for everything. Okay, so it begins, and we think we're prepared. We've imagined every eventuality, and it starts. So Black Friday last year started a little bit early for us. The excitement started about 3 hours before Black Friday, so about 9 o'clock Thursday, the night before Black Friday. An on-call person got an alert for a low power alarm. So basically, a rack in our data center had less power than it should. This triggered an alarm. And the first step is analyzing what's going on here. The guess was it was a failure of a power distribution unit, which is kind of like a fancy power bar for data centers. So a power bar failed. It's kind of a boring thing. So the panic level at this point is very low. This isn't too worrying. There's a lot more failures between this point and merchants really being affected. So first of all, every rack has multiple sources of power, so everything is still running. So the first step is really just evaluating the state of things. So this brings me to the second principle that we apply, and it's a very, very simple one on the surface. If it is important, have more than one. So this is a principle that we apply to everything, and you'll see a bunch of examples of how we apply that. So the very first one here was redundant source of power, so we're okay. So if you go a little bit further, but what if that second source of power fails? What are we worried about then? So if you think about what's running in these racks, The most important thing that's running that if it fails is going to hurt us is databases, persistent storage. So I'm going to use the examples of MySQL and Redis here, but it could be any kind of persistent storage. We have this principle of there must be 3 copies of any persistent data at all times. So we have replication change set up with MySQL and failover with Redis, where there's 3 copies of everything, and if one thing fails, we can fail over to the next one. So that gives us, if there is a failure, we can recover pretty quickly. This is still pretty scary, though, because if a writer fails, even if we have this automation that fails over to another machine, it could take a minute for the replication lag to catch up. So we still have an impact there that we want to reduce. So the other technique we use is a technique called podding. So we take every form of persistent data, we group customers into groups that we call pods. This has nothing to do with Kubernetes pods, in case you're confused. We would take 25,000 customers, they're in pod 1, they get their own MySQL, they get their own Redis, every other persistent store, they get their own. And that way, if a persistent store fails, the blast radius of that failure should be 1 pod worth of customers. So that's another way that we're trying to reduce the impact of an outage. So if we go back to our rack here that's in peril, so we have a few web servers, not too bad, they're stateless, they can go down, no problem. 4 servers that are running background jobs. Again, if those go down, they're designed to be ephemeral, it's not a big deal. But we have a MySQL, a standby MySQL, and a failover Redis instance. So if that rack goes down, we've lost redundancy. However, we're still not too panicked at this point because those are the standby instances, the primary one's okay, it's on another rack, shouldn't be a big deal. So we actually decided at this point, about 2 hours before Black Friday, we're kind of worried, but we're just going to leave it because sometimes, going from overreacting to a small problem can result in a bigger problem. So we leave it. So about 11 o'clock, the second power distribution unit fails. So now the whole rack has gone down. So this is, we're getting a little bit more worried now. So this means, again, we've lost the backup for a database, a MySQL database and a Redis database. No impact for the end user, but we are, only one failure away from a pretty major impact. So at this point, we start our incident response process. We started analyzing what our options are. So it took us about half an hour. We were a little bit slow. I think it was late at night, took people a while to gather. Finally, we made the decision we're going to do a failover. So next level of redundancy is data centers are important. So if it's important, have more than one. So we have every major critical system at Shopify is running in multiple data centers at a time. So there's what we call a shadow copy running in another data center. And we can do a failover where we move traffic over to the shadow copy and continue running there. So we decide there's 2 pods that have lost a backup persistence. We're going to fail over those 2 pods to the other data center. So we've got about 20 minutes left before Black Friday starts. So this is, we're cutting it a little bit close, but we decided to do a failover. So about 10 minutes later, we failed over. This actually worked quite well in this instance. So we switched to the second data center. We have 3 levels of redundancy left in our data stores, so we're pretty happy. So this was about 7 minutes before Black Friday started, and about 10 minutes later, we were running $1 million per minute in sales. So, we were, if it had gone downhill, we would have been at a point of our customers losing $1 million per minute. So that's the kind of stakes that were involved in that kind of situation. So we definitely dodged a bullet there. It went pretty well. My sneaky reason for that first failure was actually just explaining our architecture a little bit. So the failures are going to get a little bit worse. So third principle, redundancy at multiple levels of abstraction. So you can't just say, we need to have redundancy, so we're going to have 2 copies of our servers. You need to think about all the different levels of abstraction in your system, the people involved, the locations, the servers, the power, the internet access. Every single dimension needs to have redundancy in it. Okay, so the next 16 hours were really boring. In case you're worried I was going to do a play-by-play like every minute of the day. Pretty boring 16 hours. Giving you a couple of ways here to tell when things are going really well on a very critical period. So number 3, the worst problem we had at this point was we were seeing email throttling, which is not too unusual. So if someone buys something from an online store, it generates a purchase confirmation email. on Black Friday, we're generating so many emails that downstream providers could start to flag us as spam. So we actually have to throttle these emails and filter them out to the providers at a rate where they will not pass a threshold for that provider to mark us as spam. So we're seeing a little bit of backlog in our emails, which is not great, but it's not terrible. We're also keeping an eye on this. One of our Datadog dashboards here, we can see free RAM on our Redis servers. A couple of our Redis servers are looking a little bit unhappy. They're going down, but it's been over 5 hours. They're only halfway to exploding, so it's worrying, but we'll leave it alone. But the number one indicator that that the things were going really well for most of the day is that we were live streaming chicken coops in our war room. So one of our colleagues lives on a farm, and he was we were kind of just having some fun, and he's like, you want to check on the state of my chickens while I'm going for lunch? So he put his machine there, and we're all like watching live his chicken coop. So a little bit of a decompression during the day is kind of nice to have. So about 4:10 on Black Friday, our second failure happens, and this one's going to get a bit more exciting. We have a Redis server that runs out of memory. So just to recap some of the things we've talked about, so we have a failover server. Of course, that's out of memory too because it's got all the same data in it. So failover Redis is out of memory. The standby instance, we don't replicate the data, so it's fresh, it's fine. We still have the shadow copy in the other data center. It's fine, it's got no problems. And the blast radius, the worst case here is that one pod is affected. So it's bad, but it's not too worrying. And again, last night failover worked really well. So let's just fail over that pod to the other data center, and then we can recover the situation. So a little bit worried, not too bad. Let's do a failover. So we fail over that pod to west. So the good news, that pod recovered fine. It was fine for the rest of the day, no problems. Back in the east data center that we just vacated for that pod, the job queues were still growing. So the job queues, the most critical one, if you think from the point of view if you buy something from an online store, the payment transaction runs in a job in the background. So these job queues have payment transactions waiting to be run. So the fact that these are queuing is pretty bad. It's not the end of the world. They will get queued for a long period of time before they run if necessary, but we don't want those things queuing up if we can avoid it. So our theory here is that somehow that Redis that exploded is still causing problems. Maybe our job workers are trying to connect to that Redis and failing in some way. So we decide the next decision we make is we're going to restart Shopify essentially, the platform, which is like all of the worker nodes, all the web nodes. So this might sound like a really invasive decision, but it's actually because we're on a normal day, we're doing continuous delivery, restarts are constant. Being in a state where we're not restarting is actually pretty unusual. So we decide to do a restart. Maybe that'll clear those bad connections and we'll be able to recover. So we do a restart in our east data center. So now things go from pretty bad to the worst possible situation, essentially. So we started with about 5,000 job workers. It dropped to 2,000 initially when we had the out of memory. Then when we restarted, they all died. So every single worker is dead, and it's in a crash loop, which means as soon as it starts, it crashes, restarts, crashes, restarts, crashes. So this is really quite scary. So at this point, we don't know why. So we're still trying to figure out why. There's a couple of things we do here. So one is we start the prep. We have a sub-team start the preparation for doing a complete data center evacuation. That's sort of our last resort. At this point, we had never, ever done a data center evacuation during an incident, and we'd certainly never done it during Black Friday when, we model, we believe that each data center has capacity to handle everything, but Black Friday is the highest volume day of the year. We don't actually know for sure whether one data center can actually run everything or not. Like we believe it does, but we can't prove it. So doing a failover of the entire data center is really drastic action. So we really want to see if there's something else we can come up with here. So the other decision we make here is that bad Redis that is no longer being used because the pod has been failed over is still running. let's fail over that to the standby instances of Redis. Again, this thing shouldn't be doing anything to do with any of our system at this point, but we decided let's fail that over to a fresh copy of Redis and hope that will help clear the connections. We're a little bit desperate at this point. You can kind of guess we don't really understand the state of our system at this point, but we're making educated guess and we're taking actions one at a time to see if we can resolve them. Okay, so we do that. So some positive things. So the standby Redis is now fine. There's this fresh Redis, nothing in it. It's running happily. It's all good. The crash looping has stopped, so that's progress. So the workers have stopped infinitely, bursting into flames, but they're still not running jobs. So at this point, so it's 4:30. We've been about 10 minutes or so where jobs aren't running. And we have no idea why. Like we've done the things that we thought needed to be done. We don't know what to do. So the next few minutes were, clench all the clenchable parts and try to think of, what can we do here? Everyone's looking at their own different parts of the system and trying to figure out what to do. A few minutes go by. So I just want to pause here for a second. So this is really bad for us. We're really, really worried. But the core principle that saved us here is that from the buyer's perspective, if you're buying something from an online store during this incident, you could browse the online store, you could add to your cart, you could check out. It would appear fine to you. The only effect would be the payment job hasn't run, so you're not going to get that email confirmation saying, yeah, we got your order. So from an end user, the product is still functional. So this is a really important resiliency principle. And this is the main thing that saved us from complete disaster here, is that we designed a system that in a degraded state still behaves as well as it can. So the principle here is degraded is better than down. So whenever we can build something that in a broken state is not completely broken, that's what we're aiming for. We want it to be as good as it possibly can when that thing is, whatever that thing is unavailable. Okay, so we have this countdown clock for evacuation. That's expired. Still, we have no idea what to do. We haven't touched the system in 10 minutes. We're not we're just we're going to start the evacuation. So two things happen simultaneously, roughly. This is in our Slack war room. So the evacuation order is given. Please proceed with evacuation. And then Scott Francis, one of our senior production engineers, says, "Wait, nobody touch anything." So at this point, everyone else is confused. He's the one who knows our system the best out of anyone, and he suddenly, a light bulb's gone off his head, and he said, "Don't touch anything." So we're like, okay, we won't touch anything. 3 minutes later, 100% recovery. So yeah, you can applaud. We applauded. That's good. So at this point, we hadn't made a change to the system in about 15 minutes, and it just came back 100% to life. That's amazing, and we had a lot of questions. So I'm going to go through many of the questions we had. So this is kind of the postmortem process, what we learned out of it. So first question, why did we run out of memory in the first place? So the proximate cause here was we had an API rate limiter that had been, someone in their wisdom had decided to set it to 500% and for a particular API client, and they were allowed to make 500% of their normal request rate. And this particular API client was generating emails, so this was part of our email backlog problem. But the other question is why did we not notice anything until the thing exploded? And the other problem that came out of this was we were monitoring everything at the level of the host instead of the instance. So this graph here that I was showing you before of free RAM on the Redis server, it showed we're halfway to fine. There's 2 Redis instances on that host. The other instance is fine. One is in flames, so the server is half fine. But the key change we had to make here is changing all of the monitoring here to be instance level instead of host level, because the host level metric is just lying to me. So that was a couple of the very first things that came out of it. So second question, why did all the workers crash? So we have this principle of blast radius. One Redis instance should affect no more than 25,000 customers. Something has gone horribly wrong with our resiliency principle here, where a failure of one thing can cause a cascading effect across the entire data center. So the reason here was, so here's what should happen. So Redis fails a health check, automatically failover to the standby Redis is what should happen. If Redis failed catastrophically, or the failover failed or whatever, the worst case should have been one pod affected, all the other pods fine. So, and we have tests that verify this every day where we execute user flows with a broken Redis and we verify that the system behaves as we expect. So this is, this is how it should work, and this is definitely not what happened here. So what actually happened was the health check does a read against Redis. Reads do not fail when it's out of memory. So this is something very useful to know about Redis. So the health checked Redis. Health check says to Redis, how are you doing? Redis is like, I'm fine. And then when workers start up, one of the first things they do is they register themselves with a Redis instance to say, hey, I'm a worker, I'm going to start processing your queue. So it says, hi, Redis, I'm a worker. And the Redis says, I'm dead. So because writes fail when it's out of memory, but reads are fine. So essentially, this came down to a misconfigured health check where the health check wasn't really verifying that the system was healthy. So that was the reason why. So the workers, because we restarted the data center, each worker started up, tried to register without Redis, the write failed, and because it's happening during the worker startup sequence, it initiated the crash loop. So the final question, why was there a delay in recovery? So the thing that fixed the problem was failing over the Redis instance, the pod 0 Redis to the standby. That's what actually fixed the system, but it didn't come back for 15 minutes. So what was going on there? So this was the deepest problem, and I actually realized that I think I need another 30-minute talk to really explain this part in detail. But just to give you a high-level view, when a worker starts up, there's this crash recovery sequence where it says, I'm going to clean out the reservations from any worker that hasn't been active in 5 minutes. So it has this, each worker when it comes up goes through all of the workers that have not responded in 5 minutes and removes them from Redis. But if every single worker had been in a crash loop. So this dead worker list was every worker. Every worker starts up, it's doing the same process. So we have an n-squared recovery algorithm here in the case where every single worker is crashed, which of course hadn't happened before, so we didn't notice this inefficiency. So we had to make this crash recovery code, it's very easy to make this more efficient. The other effect here was we have circuit breakers that are protecting our servers. So if 7,000 servers start up and they all try to connect to Redis, Redis is going to explode. So what we have is a circuit breaker that says only a certain number of connections to Redis can be made at once. And then if it's exceeded, you have to back off and wait. And those circuit breaker backoffs were also good. So we had an n-squared algorithm with backoffs in the middle of it, which made the whole thing take 15 minutes, which should have taken a very tiny amount of time. So that was the reason for that very delayed effect behind when it recovered. So I just want to summarize here. So we had many failures during this day. None of them were planned, obviously not planned. None of them were anticipated. They were all novel. We had never seen these particular failures before or since. But the system, from an end user's point of view, was mostly okay. So again, as I said, the only effect for the buyer was it would have been about a 15-minute at worst delay before they got that email saying, yeah, we got your order, which could be a little bit confusing for some buyers, but really it's not the end of the world. So these principles, if it can break, it will break. If it's important, have more than one. Having redundancy at all the different levels of abstraction in your system, and designing user experiences that are as good as they can be in the face of a failure of a particular thing. These 4 principles allowed us to go from a very broken system actually did not have much impact at all for an end user. So I think I'm about out of time. I don't know if I have time for questions or not. Do I? No?
You have time for questions.
Oh, I do. Okay.
Right. So we will take a few questions. There's mics on either side as yesterday. And folks can come on up and ask some questions.
What was the Eureka moment that made him say wait?
So the question was, what was the Eureka moment that made him say wait? He was looking at graphs of our circuit breakers and seeing a pattern where they were basically going through, each worker was going through the spike where the wait times on the circuit breakers were spiking and then ring spiking and then recovering. And that made him understand that the so he didn't understand the n squared recovery algorithm part. He understood that our circuit breakers were causing the recovery to be slower than it should have. But he knew that it was recovering from that, basically.
Steve, you have a question?
Yeah, so I was wondering if you guys are using a different method to health check now to protect against that out-of-memory issue. Or
Yes.
the lack of visibility into out-of-memory.
Yeah, for sure. And this is a very, bad health checks is a very common problem. So this one just happened to have very disastrous consequences. So we spend a lot of time on health checks trying to make sure that they are accurately representing the health of a particular service. Yeah.
So do you have any detail on like what you're checking in Redis now to make sure that you can catch that before it's a problem?
I mean, so in this case, we're doing a write instead of a read. The other thing we added, actually, based on this, was we added into Semyon, which is our open source circuit breaker library, we added Redis out of memory as a recovery method in our circuit breakers. So it detects, our circuit breakers now actually detect out of memory in particular and treat it as a failure, as before those weren't recognized. So that was another thing we changed.
Question on the other side.
So in your stories, you said you had like response times of 10 minutes or less, which is damn impressive. Was that a combination of using playbooks, like practice? How did you get to, here's the problem, 10 minutes later, we're implementing a solution?
So actually, this one turned out to be, we have this incident process where we declare an incident, and when I looked at the data afterwards, we actually had a negative 15-minute MTDD in this one. The mean time to detect was negative 15 because we started an incident before it actually failed for the end user. So it was very weird. But that was entirely because it was Black Friday, our most critical day of the year. Everyone was in a room. It was really the best possible disaster response situation for us, was a big part of the speed of the response time. The basic principle we use during a response, so we have a single incident commander, as was described yesterday. Any decision, any change to the system that's made has to go through the incident commander. But then everyone else, what we call it is essentially swarming, where every single person just, what are you good at? Go look at that thing and try to understand how that might relate to this problem. So we have a room with 20 people all looking at 20 different angles on the problem. 2 people preparing for recovery, and 1 incident commander deciding about changes to the system. And just that parallel, many eyes making bugs shallow thing is really, I think, key to our response times.
We have time for a couple more, if you want to come up to the mic.
Have which tests? Yeah, so we certainly added as I said, we have these resiliency tests where we simulate particular kinds of failure cases. So we certainly added a case here where we run a user flow of the system when Redis is out of memory, and we verify that the system is behaving as. So we use for that, we have another open source library called ToxyProxy that simulates or actually causes different kinds of network-related failures. So we use those kind of tests to say, if Redis takes 1 minute instead of 1 millisecond to respond, what happens? So we added to our automated resiliency suites for this case. So this one was fairly easy to test automatically. There are other kinds of scenarios where it's a lot harder for sure.
Any other comments or questions? All right, in that case, we will break briefly, and we will be back here at 10:45. See you soon.